Hello, this is Dr. Hanaa Assil, and these are questions and answers on benzene and its derivatives, which are called arenes. This is basically for the A2 chemistry Edexcel, but it can be used to revise the reactions of benzene and its derivatives. So let's take a look at questions and discuss the answers. The first question here says, X-ray diffraction of benzene provides evidence that benzene molecules have what? Now, when they were trying to decide what is the structure of benzene, they used X-ray diffraction. X-ray diffraction is a method of pointing X-rays at a crystal, and the film or the photographic film receives these X-rays after they have been diffracted, and this information tells us the bond lengths and the structure of the crystals we're looking at. So from the X-ray diffraction, they were able to find out that benzene has equal carbon-carbon bond lengths. They found that even though benzene is known to have alternating single and double bonds, the X-ray diffraction stated that all these bonds are the same length, which indicates that the double bond is spread around, or the pi bonds are spread around the benzene, not specific single and double bonds, because if they were alternating single double, then the single bond should be longer than the double bond. But the X-ray diffraction found that all the bond lengths in benzene are equal. The information about benzene that is not provided by X-ray diffraction is the fact that, or it doesn't give any information about what? Doesn't give information about bond energies. The X-ray diffraction gives information about bond angles, bond lengths, structure, but it does not give any information about the bond energies. The delocalized electrons in benzene result from the overlap of what? Well, since the double bonds are not fixed in specific positions, they found that actually the pi bonds are spread over all the benzene ring, so that the delocalized electrons are equally distributed, so that all the bonds are the same somewhere in between a single and a double. And this is due to overlap of p orbitals, because the pi bonds are formed from overlap of p orbitals. So all the 6 p orbitals in benzene are overlap, and the delocalized electrons are spread around the benzene ring. All the bond angles in the benzene molecule are 120 degrees. Which of the following provides the best evidence? We said what tells us the bond angles and bond lengths? It is X-ray diffraction. All the others in these choices do not give the bond angles and bond lengths. The benzene molecule may be represented in two ways. So we can either draw it with a circle to indicate that the double bonds are equally spread around the 6 carbons, or we can do structure 2, in which we have single, double alternating bonds. Which of the following does not provide evidence that structure 1 is better? So which one does not tell us anything about structure? If you remember these choices, what is high performance liquid chromatography? This is HPLC. It is a chromatography method to separate components in a mixture, but it does not give any information about the actual structure of the molecule. Now, so we decided that the benzene ring has delocalized electrons around the 6 carbons, so we draw them as a circle. And if we have a molecule like this, what is the molecular formula of the compound below? In order to determine the molecular formula, think about where are the carbons and the hydrogens. Remember that each of the carbons in the benzene ring has originally 1 hydrogen. So if there is something else on it, then that replaces the hydrogen. So that this is actually the structure that is drawn, and then we can count the number of carbons and number of hydrogens and number of oxygens. You will find that this is the molecular formula of the compound C9H10O. What is the total number of delocalized electrons in anthracene? Now, anthracene is a structure in which we have 3 benzene rings attached to each other. We know that if we had 1 benzene ring, this has 3 double bonds. But what about anthracene? If I try to draw anthracene, I can either draw it like this or like this. You can't have double bonds attached to each other. We have to have alternating so that the carbon does not have more than 4 bonds. So this is this distribution of the double bond. We know that each double bond, each carbon-carbon double bond is due to one pair of delocalized electrons, one pair of shared electrons forming the pi bond. So if we say what is the total number of delocalized electrons, we can count the number of double bonds. So how many double bonds do we have? We have 3, 4, 5, 6, 7. Each double bond has a single bond and a pair of electrons shared to form the pi bond. So we're counting for each double bond, we have 2 delocalized electrons, or 2 electrons that are shared to form the pi bond. So what is the total number? The total number is 2 times 7, which is 40. Benzene burns with a very smoky flame. This is evidence for the extent to which the benzene molecule is. Well, let's talk about burning of benzene. When benzene burns in oxygen, it could give carbon dioxide and water, like normal combustion. It could give carbon monoxide and water if there is not enough oxygen in incomplete combustion. But it also gives a smoky flame due to carbon, pieces of carbon. And this very smoky flame is taken as evidence for the extent to which the benzene molecule is unsaturated. So the fact that it is unsaturated, that is why it gives a lot of smoky flame, which is due to the pieces of carbon solid formed. Benzene is sometimes represented like this, in which we have alternating double and single bonds, and we said this was a structure suggested by a scientist called Kekulé. So this is the Kekulé structure of benzene. If this were the only structure of benzene, if this was true and this is how benzene is only as this structure, what would be the total number of isomers of dichlorobenzene? Remember, dichlorobenzene means a benzene ring with 2 chlorines. So how can I put 2 chlorines on the benzene ring? I can either put it adjacent to each other, or on carbon number 1 and carbon number 3, or on carbon number 1 and carbon number 4. Now, those adjacent to each other, if the structure is a Kekulé structure in which there is a specific double bond somewhere and a specific single bond somewhere, then I would have 2 options of putting the 2 chlorines adjacent to each other. Either they are adjacent to each other with a double bond in the middle, or they're adjacent to each other with a single bond. So I would have a total of 4 possibilities or 4 possible structures. How many sigma bonds and pi bonds are there in a molecule of benzene? This is benzene. You should know that this sigma bond is the bond in any single covalent bond. So every single covalent bond is a sigma bond. Now what about the double? The double bond is made up of 1 sigma and 1 pi. So actually, if we're counting the sigma bonds, then there are all these blue bonds, and that is a total of 12 bonds. So I have 12 sigma bonds. Now, how many pi bonds? We said each double bond is 1 sigma and 1 pi. So I have 3 double bonds. That means I have 3 pi bonds. What is the organic product when benzene reacts with excess bromine in the presence of UV light? Remember, benzene can react with bromine in UV light, or it can react with bromine in presence of a catalyst, which we say is iron 3 bromide, and these are 2 different reactions. If I have UV light, then the structure that we have is this one, in which the bromine is added to each carbon in the benzene ring, and there is no longer double bonds. So this is actually cyclohexane. It's no longer a benzene ring. So remember, if I have benzene, excess bromine in presence of UV light, this is the product that is obtained. When excess bromine reacts with benzene in presence of UV light, so this is the reaction that we just talked about, what type of reaction is this? Well, this is free radical addition. So it's as if I am adding the bromine to all the double bonds in the benzene ring. What is the product when benzene reacts with fuming sulfuric acid? Now, this is another reaction of benzene. If I react benzene with fuming sulfuric acid, this is a method of adding the sulfonic group on the benzene ring, the SO3H on the benzene ring. So this is the product that I get. So this is benzene with concentrated sulfuric acid with SO3, sulfur trioxide. Benzene reacts with fuming sulfuric acid. What is fuming sulfuric acid? You should know that fuming sulfuric acid is concentrated sulfuric acid containing dissolved sulfur trioxide, and we said this puts an SO3H on the benzene ring. What is correct for the reaction of bromine with phenol when compared with benzene? So if we have bromine reacting with phenol versus bromine reacting with benzene, so phenol would be what? You should know that phenol is a benzene ring with an OH on it. So if we have the OH, the electrons on the oxygen, lone pair of electrons on the oxygen in phenol are delocalized over the benzene ring, and this makes phenol more reactive. So we have to know that phenol is more reactive when the lone pair of electrons on the oxygen are spread around or delocalized over the benzene ring. This makes this benzene ring have more electrons available for reaction. So actually the phenol is more reactive than benzene because it has higher electron density due to the lone pair of electrons on the oxygen being delocalized over the benzene ring. So when phenol reacts with excess bromine water, what is the product? Now, when phenol reacts with excess bromine, This is the kind of structure we have. Remember, phenol is a benzene with OH on it. Now we react it with bromine. We're going to put bromine on. If the carbon that has the OH is regarded as carbon number 1, then I am putting bromine on carbon number 2, carbon number 4, and carbon number 6. So this is 2, 4, 6 tribromophenol. That's what we get. Which reagent and catalyst will convert benzene into phenylethanone? You can see phenylethanone. We put the C double bond O CH3 on the benzene ring. Now, if I have this kind of reaction, you should know that this kind of reaction is electrophilic substitution. How does it occur? I need what to react? I need this group CH3 C double bond O with a Cl on it. So what I want is ethanoyl chloride. That's my reagent. The catalyst in all of these cases is aluminium chloride, because the aluminium chloride will accept electrons and take the chlorine away from the ethanoyl chloride, so that carbon becomes a positively charged carbon, while the aluminium now has 4 chlorine, so it has a negative charge. And what happens in any electrophilic substitution reaction of benzene is that the electrons from the benzene attack the positively charged species, which we call an electrophile. So a substance that has a positive charge that is reacting with the benzene, this is an electrophile, and this adds that group to the benzene ring. But that carbon originally had a hydrogen there, so we're going to remove that hydrogen and give the electrons of its bond to the benzene ring and get our product, in this case plus HCl. This is the basic mechanism for electrophilic substitution in the benzene ring. Aluminium chloride catalyzes the reaction. We just said, for the reaction to start, I am starting with something that has a chlorine on it. Now, the aluminium chloride will act as a catalyst. This is because the aluminium chloride does what? The aluminium chloride is an electron pair acceptor. So it accepts an electron pair from the chlorine, breaks it off from the chloro compound species that we're reacting to form a positive electrophile, and then this positive electrophile can go on and react with the benzene. Chlorine reacts with methyl benzene in presence of UV light. Again, if we're saying in presence of UV light, then in this case we're going to have this product. So if I have methyl benzene means just a benzene ring with a methyl group on it, a CH3 group on it. Now we're reacting that with chlorine. Well, in presence of UV light, then we're going to replace one of the hydrogens of the methyl group with a chlorine. When benzene reacts with a mixture of concentrated nitric and sulfuric acid, so if we have benzene and we react it with concentrated nitric and sulfuric acids, this again is an example of electrophilic substitution, in which the electrons from the benzene attack the nucleophile so that the concentrated nitric and sulfuric form this nucleophile, in which we have NO2 with a positive charge. The electrons from the benzene attack the nitrogen that has a positive charge and adds that to the benzene ring, and the hydrogen that was originally on that carbon will be lost and the electrons are given back to the benzene ring. So again, this is an example of electrophilic substitution. How many isomers containing a benzene ring are there with the molecular formula this? Well, let's look at this. This is something that has a 6 carbon, so that's the benzene ring, with 2 nitro groups and 1 hydroxyl group. So we're trying to draw all the possible structures in which we have a benzene ring, and on it we have 2 NO2s and 1 OH. So how can we draw them? I can draw it like this, so that this is 2,4-dinitro phenol, or like this, so this is 2,3. Remember, the OH, the carbon with the OH is carbon number 1. So here these are 2,3-dinitro, or 3,4-dinitro, or 2,6-dinitro, or 3,5-dinitro, or 2,6. So these are all the possible ways that you can put 2 nitros and 1 OH on a benzene ring. So I have 6 possible isomers. Can we see all of that? Okay. The reaction of ethene with bromine. Of course, ethene is an alkene. It reacts with bromine under normal laboratory conditions. At room temperature, you don't need to do anything to it. It will react quickly. But the reaction of benzene with bromine to form bromobenzene requires heat and catalyst. The best explanation for the difference in reactivity is that, of course, we said that the benzene ring has delocalized electrons. And that means the double bonds are not in a fixed position, alternating double single. They are spread around the benzene ring, so the electrons, we say, are delocalized in the benzene ring. What does this do to the reactivity? This makes the benzene a very stable compound, and it doesn't want to react. So this, we say, results in a kinetic barrier, because this will make the energy of activation high. So it has high energy of activation, so the reaction is not easy, and that's why I need heat and catalyst and so on. So remember, we said the benzene ring does not react easily because the reaction has high activation energy. High activation energy is referred to as a kinetic barrier. So it results in a kinetic barrier to intermediate formation. So it doesn't form the intermediate easily. It does not react easily. When bromine water is added to benzene, no reaction occurs. However, when bromine water is added to phenol, aqueous solution of phenol, it reacts. We get a white precipitate with an antiseptic smell. What is the explanation for this? So we're basically saying that phenol is more reactive than benzene. Why is phenol more reactive than benzene? We said because phenol is something that has an OH, so the lone pair of electrons on the oxygen can be spread around the benzene ring, or we say can be delocalized around the benzene ring, and this makes the benzene ring in phenol more activated, or it reacts more easily. Which statement explains why bromine reacts more readily with phenol than benzene? Again, why is phenol more reactive? We said this is because the lone pair of electrons on oxygen in the phenol is delocalized into the ring. So this means the phenol has more charge density, so it has more electrons available to attack an electrophile. Which of these could not be formed when excess benzene is heated with trichloromethane? This is trichloromethane, and we said if we react this with benzene, what happens is the benzene will replace the chlorine molecules or the chlorine atoms. So how many chlorines do we have? We have 3 chlorines, so we can replace only 3 chlorines. So we can put only 3 benzene rings. We cannot put 4 benzene rings on that molecule. So this is the structure that could not be formed when we react benzene with trichloromethane. Give the equation for the reaction of benzene with bromine. Again, we said if we react benzene with bromine, and again, we're going to remind you that the catalyst in this case is anhydrous iron 3 bromide. What happens is we put bromine on the benzene ring, and this is electrophilic substitution reaction. Now, the question says include state symbols. What is the state of benzene? You should know that benzene is a liquid. Bromine also is a liquid, and the bromobenzene formed is also a liquid. The other product here is HBr, and this comes out in the form of a gas. 3 C6H6 structures proposed in the 1860s are shown. So in the 1860s, they didn't really know what was the structure of benzene. So these were some structures that were proposed. The delocalized model for the structure of benzene, that's the one in which we have a circle written in the middle to indicate that all the electrons are delocalized on the benzene ring. This model has been accepted since the 1930s following the study of its X-ray diffraction pattern. So we said from the X-ray diffraction pattern, they decided that this is the structure of benzene. And the understanding of electron delocalization, the fact that we started to learn that the electrons of the pi bond can be delocalized around the benzene ring. The Dewar and Ladenburg structures that are shown above have since been isolated as stable compounds. They were able to prepare the Dewar structure and the Ladenburg structure. But there is no compound with the Kekulé structure. They were not able to isolate or to make a compound that has this structure. Describe a chemical test, including the result that could distinguish the Dewar from benzene. Where is the Dewar? The Dewar is the one that has double bonds. And the benzene, we said the double bonds are delocalized around the benzene ring. So which chemical test can we use to distinguish between them? What was the test for double bond, or the test for alkenes, or the test for unsaturation? That was add bromine water. The one that has double bonds, that's the Dewar structure, would change the bromine from orange to colorless. But with benzene, there will be no change. State one similarity and one difference you would expect in the proton NMR spectrum, the low resolution proton NMR spectrum of Ladenburg and benzene. Do you remember the proton NMR? Proton NMR spectrum indicates, or it has peaks for different protons in different environments. If we look at the Ladenburg, you can see that all the protons are equivalent. So all of them give only a total of one peak. In benzene also, all the protons are equivalent. But in the NMR spectrum, the peaks will have different chemical shifts. So the similarity between them is that they both have one peak. But they have different chemical shifts. So from the data booklet, you will have this from your data booklet, that the Ladenburg is a proton attached to carbon, so that would have chemical shifts at about 0 to 2 ppm, while the one in benzene, this is the one that has a RH or arene ring or aromatic ring with a hydrogen on it, and in this case the chemical shift is about 6.4 to 8.4. Explain how X-ray diffraction shows that benzene has a delocalized structure and not a Kekulé structure. Do you remember what we said about X-ray diffraction? We said if we're comparing the benzene to the kekulé structure, if we do the X-ray diffraction of benzene, we said the X-ray diffraction is something that gives us an idea of the bond lengths and the bond angles. They found that all the carbon-carbon bonds in benzene are the same length. If it were a kekulé structure with alternating single-double, then the single should be longer than the double. So the fact that all of them are the same length means that all of them are equivalent, so they are all somewhere in between, the bond lengths are somewhere in between single and double. Methylbenzene, which is benzene with a CH3 group on it, reacts with ethanoyl chloride in presence of the catalyst aluminum chloride to form a mixture of organic products in which you add that ethanoyl group on the benzene ring. Draw the skeletal formula of 3 different arenes with the formula of CH3CO and then a benzene ring with a methyl group. So in how many different ways can you draw, actually he wants 3 of them. We want to draw a benzene with a methyl group on it and then attach a CH3CO group to the benzene ring. So these are the 3 different possible structures in which we have a methyl group and a C-double bond OCH3 attached to the benzene ring, and he wants skeletal, so you need to draw it in the skeletal form. So this is how we draw it. And then the question says carbon-13 NMR spectrum of one of these arenes that we just drew is shown. So we have a carbon-13 NMR with how many peaks? We have 3 on the left, and then we have 1 in the middle that says that it is actually 2 very close to each other. And then we have 2 on the right, so this is a total of 7 peaks. And the question is, which of these structures that we drew has 7 peaks in the carbon-13 NMR? That means it has 7 different carbon environments. Identify compound X and use the number of peaks to justify your answer. So which of these has 7? The one on the left. Let's start with the one on the left. How many different carbons do we have? Actually, all of them are different, so we have a total of 9. So if it were this structure, we would have 9 peaks. The one in the middle, also all the carbons are different, so we should have 9 peaks. But the one on the right, it is symmetrical. So we have 2 on the benzene ring on the right are the same as the 2 on the left, because this is a symmetrical molecule. So this is actually the structure of X, and this is because it has 7 peaks which agree with the carbon-13 NMR spectrum. Complete the diagram, including curly arrows, to show the mechanism for the formation of compound X in this reaction. And this is a common question. We need to learn how to draw the mechanism of electrophilic substitution of benzene. We start with a compound that has chlorine. So here we're starting with CH3COCl. It reacts with the aluminum chloride. And we said, if I want to write the mechanism to get this compound, this is what we start with. The aluminum chloride, we said, acts as electron pair acceptor. It takes electrons from the chlorine, and this breaks the chlorine off from the original reagent to form an electrophile with a positive charge. Then we start the mechanism. Electrons from the benzene ring attack the positive electrophile. This attaches the compound to that carbon, but that carbon originally had a hydrogen on it. So we remove that hydrogen, and the electrons of the bond are used to return the benzene to its original structure. Remember, when the electrons attack from the benzene, then the benzene becomes a positively charged species. So this is how we draw it. And then to return it back to its original structure, we use the electrons from the bond to the hydrogen. Now, it says include an equation for the regeneration of the catalyst. How are we going to regenerate the catalyst? This is when the aluminium with 4 chlorines break off one of its chlorines to remove the hydrogen, and the products are the H with the Cl plus the aluminium chloride, which is the regenerated catalyst. Benzene reacts with bromine in presence of iron 3 bromide to form bromobenzene. Draw the mechanism for this reaction, including the formation of the electrophile. So we're starting with what? We're starting with bromine, and you should realize that what happens is, first of all, what is the catalyst? It's iron 3 bromide. This accepts electrons from one of the bromines, so now we have a slightly positive bromine that is attacked by the benzene ring, and we have the benzene with a positive charge. We added a bromine to the carbon, but that originally had a hydrogen. Now we're going to use that iron bromide species to remove the hydrogen and give back the electrons of the bond to the benzene ring. So I get bromobenzene, and my other products are HBr and the FeBr3, which is the regenerated catalyst. Then this question says the structure shown was suggested for benzene by a chemist called Kekulé. So this is the structure in which we have alternating single and double bonds. Benzene is now thought to have a delocalized structure, which is the one in which we said that the electrons, the electrons of the pi bond are delocalized around the benzene ring. Evidence for the delocalized structure of benzene includes that only one structure for 1,2-dichlorobenzene is present. So this is 1,2-dichloro. We can have 1,4, which is the para, that's 1. We can have 1,3, which is in the middle there. But if we want to put 2 chlorines adjacent to each other, if the Kekulé structure is correct, we said we should have 2 of them. One in which the 2 chlorines are next to each other with a single bond in the middle, or the 2 chlorines are next to each other with a double bond in the middle. Now, evidence for the delocalized structure of benzene includes the fact that we have only one structure for 1,2-dichlorobenzene, not these 2. It's just one. That means that the bonds are equivalent. And analysis of X-ray diffraction images of benzene. Explain why each of these makes the delocalized structure more likely to be correct than the Kekulé structure. So, if we're looking at the isomers of dichlorobenzene, the isomers in which one has single bonds between the carbon atoms bonded to chlorine and the other has a double bond, this has not been found. So we don't have these 2 options of 1,2-dichloro. It's just one of them. So we said this means that the bonds are equivalent in the benzene ring. Then the X-ray diffraction, you should remember that we said the X-ray diffraction shows that all the bonds in benzene are the same length. If it were alternating single and double, then the single and the double would have different bond lengths. Benzene can be converted to ethyl benzene. So we can put an ethyl group, C2H5, on the benzene in an electrophilic substitution reaction. Write the mechanism for this reaction, including the step involving a catalyst in which the electrophile is formed. You should know that in order to put the ethyl group on the benzene ring, that means we're starting with the ethyl group attached to a chlorine or bonded to a chlorine. Now, what is our catalyst? We said our catalyst is aluminium chloride, which acts as an electron acceptor, removing the chlorine from the reagent to form a positive species, which is the electrophile, and aluminium with 4 chlorines, which is a negative species. So, the benzene ring now attacks the positive. Again, electrons from the benzene ring are used to make a bond to the positive electrophile. That carbon originally had a hydrogen, so we're going to remove that hydrogen and put the electrons of its bond back to the benzene to remove the positive charge in the benzene. So now our products are the ethyl benzene and HCl, and we regenerate the aluminium chloride catalyst. This is the basic mechanism for electrophilic substitution of benzene ring. Please learn this. We usually start with a species that has a chlorine on it. Then the catalyst removes the chlorine to form a positive electrophile, which is attacked by the electrons from the benzene ring. Compare and contrast the reaction of benzene with bromine with reactions of cyclohexene with bromine and phenol with bromine. Include reasons for any differences. Detailed mechanisms are not required. So let us think about reactions of benzene, cyclohexene, and phenol with bromine. So if we're looking at benzene and cyclohexene and phenol, they all react with electrophiles. So we're going to react each of them with an electrophile, which is a species that has a positive charge. In benzene, a catalyst is needed. So when we're reacting benzene with bromine, we need a catalyst. It's usually iron 3 bromide. This is because the benzene has delocalized electrons. So we say this makes it kinetically stable with high activation energy. So it undergoes electrophilic substitution to form bromobenzene. If we heat it in UV light, it gives a different product. We said if we have benzene in UV light, the bromine or the benzene forms a species in which we add bromine to each of the carbons to form hexabromocyclohexane. What about cyclohexene? Well, in cyclohexene, we have a double bond. So the pi electrons of the double bond are not delocalized. They undergo electrophilic addition with bromine, just like any alkene. This forms easily, it reacts easily to form 1,2-dibromocyclohexane. What about phenol? In phenol, we said the reaction is faster than benzene. This is because the lone pair of electrons on the oxygen is, again, delocalized, overlaps with the delocalized electrons in the ring. So we say phenol has more electron density, so it is more likely to do electrophilic substitution, in which it uses the electrons to attack an electrophile or a positive species. So as a result, phenol, when we react it with bromine, it reacts at room temperature, and the product is 2,4,6-tribromophenol. Phenol reacts with dilute nitric acid at room temperature to form a mixture of 2-nitrophenol and 4-nitrophenol. The reaction is an electrophilic substitution. Again, if we say draw a mechanism for the reaction to form 2-nitrophenol and assume that we already have the electrophile, NO2 plus is already done. So all we need to show is the fact that electrons from the benzene will attack the positively charged nitrogen in the electrophile. This adds the NO2 to the benzene ring, but the carbon there already has a hydrogen. And note please that the benzene ring now has a positive charge delocalized around it. Now we use the electrons from the hydrogen to remove that positive charge and return it back to a benzene ring. Benzene requires a mixture of concentrated nitric acid and concentrated sulfuric acid at 60 degrees Celsius to form nitrobenzene. Explain why phenol requires milder conditions for nitration than benzene. Why is phenol more reactive? Again, we said, remember that we said the phenol is more reactive than benzene. Why? Because the lone pair of electrons on the oxygen overlaps with the delocalized pi electron cloud in the ring. This makes the ring in phenol have higher electron density, so the ring is more likely to do electrophilic attack on a positive electrophile. This question says some thermochemical, X-ray diffraction, and bromination information on benzene and cyclohexene are shown. So we have information about enthalpy of hydrogenation of benzene and cyclohexene, bond lengths from X-ray diffraction, and reactions with bromine. Explain how all this information provides evidence that the electrons in the pi bonds of benzene are delocalized. So, what was the information given? There was thermochemical data in which we're given the value for enthalpy of hydrogenation of benzene and cyclohexene. Now, if we have benzene with 3 double bonds, separate, alternating double and single bonds, then it should be 3 times the enthalpy of hydrogenation of cyclohexene, which has only 1 double bond. But as we see from the data, actually the benzene value for enthalpy of hydrogenation is not 3 times the one for cyclohexene. So if we say benzene has 3 double bonds while cyclohexene has 1, then the enthalpy of hydrogenation of benzene should be 3 times that for cyclohexene. So actually the value should be minus 360, not minus 200 and something. So the actual is less exothermic than expected, and that means the double bonds are not fixed like this with alternating single and double. It is delocalized, so it is somewhere in between a double and a single bond. Now, from the X-ray diffraction data, what do we have? It says that the benzene ring, all the bonds are the same and they all have the same bond length. But for cyclohexene, the length of the bond that is single is different from the length of the bond that is double. So from the X-ray diffraction data, in cyclohexene, single carbon-carbon bonds are longer than the double bonds, while in benzene, all the bonds are equal in length and longer than the one that is double. So that indicates that the electrons are delocalized so that all the bonds are the same length and they are in between a single and a double. Bromination. If we want to add bromine to benzene, we need to use iron 3 bromide as a catalyst and heat. But if we're reacting cyclohexene, we only need room temperature. So remember, adding bromine to a benzene ring or reaction to form bromobenzene, I need anhydrous iron 3 bromide as a catalyst and heat. But for cyclohexene, this occurs at room temperature and this gives the 1,2-dibromo product. So from bromination data, it's obvious that benzene is less reactive. It requires a catalyst, and this is because it reacts by electrophilic substitution, not by addition reactions like cyclohexene. This question is about naturally occurring substance 2-hydroxybenzoic acid. So this compound is called 2-hydroxybenzoic acid. Again, give the molecular formula of this compound. Again, in order to determine the molecular formula, I look at where are carbons and hydrogens. So if I draw it out, it's actually like this. And then I can count the total number of carbons, hydrogens, and oxygens. Remember, this is what we mean by molecular formula. Okay. Then the question says the main chemical present in oil of wintergreen is methyl 2-hydroxybenzoate. That is the compound on the right. Methyl 2-hydroxybenzoate, which is a liquid at room temperature. Give the chemicals and conditions needed to prepare this compound from the 2-hydroxybenzoic acid that we had, which is the one on the left, in a single step. So I want to change the 2-hydroxybenzoic acid into that product that has a methyl what? This is what kind of compound? This is, you should realize, is an ester. With a C double bond O, OCH3, this is an ester. So we're trying to change acid into ester. I react it with an alcohol. So I need methanol in presence of concentrate sulfuric acid and heat. This is how we do esterification of an acid. Okay. A student suggested that caffeic acid, which is the structure given, could be synthesized by an electrophilic substitution of 1,2-dihydroxybenzene. What is 1,2-dihydroxybenzene? That's that compound. We need to use it to make caffeic acid, which is the structure given. Draw the mechanism for this electrophilic substitution, including the formation of a suitable electrophile. So I want to put on that benzene ring that has 2 hydroxyl groups, I want to put what? I want to put this group. And that means my electrophile would be this group with a Cl. That's how we make the electrophile. The group we want to add, we put a Cl on it, react it with the aluminium chloride catalyst. This removes that chlorine and forms a positive charge on that carbon, and aluminium with 4 Cls now has a negative charge. Now the benzene ring will then attack the positively charged carbon, attach it to the benzene ring, but that carbon already had a hydrogen, so the AlCl4 minus will be used to remove that hydrogen, return the electrons of its bond to the benzene ring so that we get the product. Deduce the structure of quinic acid. So quinic acid is something that combines with caffeic to form this product, chlorogenic acid. Caffeic was this one. So this is caffeic acid. Now, what is the structure of the compound that will react with this to form chlorogenic acid? Of course, if I look at that compound, chlorogenic acid, what am I adding? I'm adding this group to the caffeic acid. And the caffeic acid already has an acid group there, so I need that group with an OH, so I need an alcohol group there so that the alcohol reacts with the acid to form that ester linkage between the two rings. Are we okay? Mandelic acid can be synthesized from benzene in the sequence shown below. Please get used to synthesis of compounds starting with something like benzene. So we're starting with benzene and we're trying to make something called mandelic acid through several steps. Use your knowledge of electrophilic substitution to suggest the identity of the electrophile in stage 1. What happened in stage 1? We added to the benzene ring, we added this group, which is an aldehyde group, the C double bond OH. we need to add that to the benzene ring, and that means we must have started with something like this that has a chlorine, and then we remove the chlorine, so the electrophile would be that carbon with a positive charge. Write the mechanism of electrophilic substitution. Again, using that electrophile, what happens? The electrons from the benzene attack the positively charged carbon. We attach that to the benzene ring, but the benzene now has a positive charge. Then we can remove the hydrogen, return the electrons of its bond to the benzene, and we get the product. State the reagents and conditions for stage 2. This was stage 2. What are we doing? We're changing aldehyde to cyanohydrin. How do we do that? You should remember all the reactions. We react the aldehyde with sodium cyanide and HCN. This will add the C triple bond N group to the C double bond O, and this forms a cyanohydrin. State the reagent required for stage 3. What is stage 3? We're changing the cyanohydrin into an acid, so we're changing the nitrile group, the C triple bond N, into acid. How do we do that? We use aqueous acid, aqueous HCl, and this causes hydrolysis, and we form the acid from the cyanide group. A student suggested that eugenol, can you see the structure of eugenol, could be prepared by electrophilic substitution of 2-methoxyphenol. Can you see 2-methoxyphenol? Use your knowledge of electrophilic substitution to suggest the electrophile that was used. So what did we add on the benzene ring to change 2-methoxyphenol to eugenol? We added that part on top. So our electrophile will be that part with a positive charge on the carbon. Suggest an organic compound that could be used to produce the electrophile. How do we get this? We said we have a chlorine bonded to that carbon so that the aluminum chloride can remove it and form a positive charge on that carbon. And that's the end of this video. I hope you find it useful. Please like the video, share it with others so that they can benefit from it. And thank you for listening.